Today we're going to take a look at a couple of sections. The first one is 3.1, which is Extrema on an interval. I really hope you've printed off notes for today because there's a lot of writing and we're not going to take time to write everything down if you haven't, so you'll want to just kind of fill in some of those blanks. Some definitions of extrema. So let f be defined on an interval containing c, an interval I containing c. F of c is the minimum of f on I when f of c is smaller than all of the f of x values for x in I. And you can see the picture that I've gotten drawn over here. That red mark C on the right-hand side with a dot below would be a minimum. And the definition is telling you that the reason that it classifies it that way is because all of the other y values, or f of x values, are bigger. And then f of c would be a maximum if it were the bigger of all the values on that interval. It's worth noting that it doesn't have to be the smallest point on the whole graph or the biggest point on the whole graph, just on an interval nearby. So when we're talking about extrema, we're looking at some sort of a neighborhood around our point. It's the lowest point in that general area. When we're working with this, there's a couple of different types of extrema. The extrema that I just referenced is actually called a relative extrema. If it's the absolute smallest in the entire graph, it's called an absolute extrema. So the maximum and minimum values on the interval are extreme values, or extrema of the function on the interval. They're also called absolute maximums and absolute minimums, or some resources will call them global maximums or global minimums. So there's two types of extrema, ones that are in a nearby area and ones that are absolute. The extreme value theorem says that if we have a closed interval, right, like it has a starting point, it has an ending point. If I were writing an interval notation, I'd be using the brackets, not parentheses. If I have that kind of an interval, there will always be an absolute biggest value for y and an absolute smallest value for y. Okay? That's what the extreme value theorem says. And if you kind of can imagine this picture over here, I'm going to flip back over to it. I'll come back to this slide, I promise. But if you imagine this picture that I've drawn here without, I don't know why this has got a fuzzy dot right here on the end, but if you imagine looking like this, where it starts and it stops at those endpoints, there is definitely a location where it is the smallest value, and it happens to be at that sort of valley point C. But there's also a place where it has the absolute biggest value, and it happens to be on the left-hand endpoint. So these extreme values can occur at valleys or at peaks, or they can occur at endpoints of intervals. All right? But they will always occur somewhere if the interval's closed. Now, if the interval's open, imagine that you had like an asymptote, so you couldn't actually reach a specific value, then that falls apart, right? Because the interval's open, and I might actually have an asymptote or an open circle or something there instead. But if the interval's closed, then the extreme value theorem applies. I referenced this before, although I didn't call it this. These extreme values that occur at these valleys or these peaks are called relative extrema. Sometimes they're called local extrema. So if there's an open interval containing C on which C is a maximum or a minimum value, we can say that F has a relative maximum or a relative minimum there. So let me draw a picture just to give you a reference point of what this is and is not saying. So if I had a graph that did this, it can have open circles, it can continue on and go to infinity, I don't care. There is a point here, it's about right here the way I've drawn it, maybe a little bit over to the left, where it's in a neighborhood, in a closed by area around it, it's the smallest value. So it would be a relative minimum point. It's not the smallest point on the graph. Clearly there are points, over here and so forth that are lower y values. But in a local area around where it is, it would be an extreme value. It would be a local minimum. And this point, the second one I plotted, would be a local maximum or a relative maximum. Okay, it's all about what you're comparing. So I always like to tell the story. We moved to Ohio, and my mom came to visit. And my family were rather short. My mom would tell you that I'm tall. I am 5'4". And she thinks I'm tall because I am the tallest female in my family. Yeah, I know, right? Jalen's like, yeah, so, yeah, like that's just it. My mom thinks I'm tall. So she shows up and we have this youth pastor position. My husband's a youth pastor. Every single one of our middle school and high school students are taller than me, all of them. Middle school students, all of them, even the boys. And it was this eye-opening experience to my mom that maybe I'm not tall. She had no idea. And so it's all about the comparison, right? So like in her world, where she lives with the people she's around all the time, my family, I'm tall. It's all relative. You've heard that phrase before, right? It's all relative. In her world, I'm tall. But when we put me in this other setting, this teenager setting in this case, I was not. I was quite short. And I'm quite short in comparison for the most part with this class. A few of you are close to my height or shorter, but most of you are taller than me, and that's okay with me too, by the way. So it's all relative. So that's what we're looking at for those kinds of numbers. These places where we have potential points, where there's these maximum, these curvatures, or these lower points, these valley curvatures, these are places that are called critical numbers. They're potential places where we have sort of, what about this point? Is this one a local minimum? Is this one a local maximum? So if we have this function and it's defined at C, if f of c is 0, okay, or if f is not differentiable, that should say f prime of c. That's a typo. I wonder how long that's been on my slides wrong. Please make that fix. Thank you. If f prime of c is 0, that is the derivative is 0, or if the function is not differentiable, so we've talked about places where it's not differentiable, like these sharp turns, right? Or potentially a place where there's a jump in the graph or a hole in the graph, those not differentiable spots, then those spots are sort of contenders. They're critical numbers. They may not be, but they may be relative extrema. They're points for us to check, to test, to take a look at. And the reality is that these relative extrema, while they don't always happen at each one of these critical numbers, they do only happen at critical numbers. They're the only possible choices. They may not all work, but they're the only ones where they might work at all. And that's what the Theorem 3.2 is saying. If we do have a relative extreme point, it's happening at one of these critical numbers. I promise we're going to get to some problems very soon. A lot of definitions at the beginning of the chapter. Okay, so one more set, and then we're going to do some examples. These are guidelines for actually finding extrema. So we're going to be finding extrema in this section. So the first thing that we have to do when we're looking for extrema is we have to consider the places where we have critical numbers. In particular, places where either the derivative doesn't exist, that's what we saw back here on this definition at the top, the derivative doesn't exist, or where when we take the derivative and we set it equal to 0, we have x values. So places where the derivative is 0 or places where there is no derivative. The graph does not have a derivative. After we find those critical numbers, we evaluate the function at each of them. Plug those x values back into the original function. We also test the endpoints. We're working on closed intervals at this point. We're talking about the endpoints because those are also potential candidates for having absolute extreme values. And then the smallest of these values is the absolute minimum. And the biggest of these values is the absolute maximum. Okay, so I feel like we desperately need to do an example. What do you think? Yeah. Lots of writing, lots of talking, no math. Okay, so let's do some work. Here's an example. We're going to find the critical number. So very limited question. It's not asking me to do all of this stuff. It's just saying, step 1, just find the critical numbers. So first of all, what kind of a function is this? What do we call it? It's cubic. Generally speaking, you can call it a polynomial as well, right? And one of the things that we learned early on about polynomials is what about their differentiability? Remember? Somebody said something. Where are they differentiable? It's not a trick question. Everywhere. Thank you so much, Emma. Yes, everywhere. There are no places where we have vertical asymptotes or disconnects, right? There's none of that going on. I don't have any sharp turns. These are smooth and continuous. Polynomials are wonderful. All right, so there are no places, like back up here where it says where it is not differentiable. That doesn't happen for a polynomial. So the only thing I'm going to be looking for is the other part of this particular definition, which is the f prime equaling 0. So let's take a look at finding the derivative. So you guys have gotten really good at finding derivatives, at least I hope you have. What's the derivative of x cubed? 3x squared. And what's the derivative of negative 3x squared? Negative 6x. Okay, so would you like to hear some really good news? The derivatives are about to be lots more simple. That was really terrible grammar, but we're working with simpler stuff from this section. Our derivatives are going to be mostly simple rules or simple product rules. We're not going to be getting the messy, ugly, horrible stuff from your gateway. That's not what's going to happen as we're working through these problems, okay? Nobody's even going to say like, whoo, yay, hallelujah, nothing? Yeehaw. Yeehaw, thank you so much. All right, so our goal is to take the derivative and to find where it's 0. So if I set this equal to 0, this becomes an algebra problem now, right? How do I find where 3x squared minus 6x is equal to 0? A factor. A what? A 3x. You're right. So if I factor out 3x, what will I be left with? 3x minus 2. Fabulous. Everybody good with that? Yeah? Cool. And then we set each factor equal to 0 to solve. Right? So x is 0 and x is 2. And those are my critical numbers. Okay, is everybody good with that? Finding critical numbers is examining where the derivative is equal to 0 and if there's any locations that the derivative doesn't exist, and this one didn't have any of those. So we're done.
Well, we always need to write it like x equals.
Yeah, if it said you wanted you to find a critical point instead of a critical number, they would be looking for the xy ordered pair, and you would take each of these x values and put it back into the original function. So that's a different possibility. I can't remember if your book or if WebAssign has you do any of those, but they could. Yeah, good question. All right, let's try another one. Directions are a little different on this one. This one actually asks us to find the absolute extrema. All right, so what does that mean? Well, that's where this guideline for finding extrema business came in. So the problem starts out just like the last problem. Step 1, find the critical points. So again, this is a polynomial, yeah? Yeah, it is. So finding the critical points here means I'm taking derivative setting equal to 0 because there aren't any places where the derivative doesn't exist. So this derivative is what? What is the derivative of negative x squared? Negative 2x, and then, and then the 5 goes away, right? Okay, if I set this equal to 0, what's x going to equal? No factoring on this one. This one's even simpler. 3 over 2. Is everybody good? Okay, so I've marked this as step 1 because we're going to do all of those steps that it mentioned on the guidelines. So step 1 was finding the critical numbers, and there's only one. Okay? Step 2 says to evaluate f at each critical number. So that's what we would do, Frankie, on the one that you asked about, saying, is that how we'll always write our answers? So step 2 is exactly what you would do if you were finding the critical point. So on step 2, we're actually going to evaluate at 3/2. You're welcome to grab your calculator, but we're going to be plugging 3/2 into the original function.
Can it be negative?
It's positive because you move it to the other side. Yeah, it's okay. So I'm going to let you guys calculate that for us. It wouldn't be a bad idea to put it into y equals, put in 3x squared, negative x squared plus 3x minus 5, and then use your table, because we're going to evaluate a couple more things here in this function in a moment. What happens when you plug in 3/2 or 1.5? Okay, and I'm going to write it as a fraction just because I already had fraction written, but decimal would be fine on that one. It's negative 11/4. So if you wanted to use decimals on this and use 1.5, and then what did you say it was, right, Anthony? 2.75?
Yeah.
Or negative 2.75. Either of those answers are fine. Okay, so that's step 2. Step 3 says to evaluate the endpoints, and the endpoints were given in the problem up here as negative 2 to 1. So we need to find what is f of negative 2 and what is f of 1. So step 3. So when I plug in negative 2, what do I get? Always evaluating back in the original function. It is negative 15. Good job. And at 1? Negative 3. Okay, everybody good so far? Okay, we've done steps 1, 2, and 3. Step 4 says the smallest or the least of these function values you just got will be your absolute minimum, and the greatest one will be your absolute maximum. So, looking at these 3, which one is the least? Yeah, f of negative 2, which is the negative 15. So when we're in step 4 is really like giving our answer. It's the interpretation. We have an absolute minimum of negative 15, and it happens at x equals negative 2. Right? That's the smallest value. Which one's our biggest value? Yes, ma'am.
Where did you get the negative 15? Did you put it back into the equation?
That's what this notation means.
Okay.
Oops, I'm not using the right symbol, but this one. It means the original function, plug in negative 2.
I plugged in the negative 1 and spit out negative 9.
Because it's not negative 1, it's positive 1. This interval says that I'm going from negative 2 to positive 1, so you probably have a sign off, yeah. Okay. How about these other 2 values? Which one's the biggest? Which one? The one that happens at 3 over 2. Yeah, it feels weird because we're talking negatives, but negative 2.75 is a bigger number on a number line, right, from right to left, or left to right, whatever, than the negative 3. So as awkward as it feels because it's still negative, our absolute maximum, and it's 11 over 4, negative 11 over 4. You could write negative 2.75, and it occurs at x equals 3/2. Was it 3/2? Hang on just a second. Oh, there's one weird thing going on. I didn't notice until just now as I was writing it down because that didn't feel quite right. Did you notice this interval? I don't even have this in my notes. What's that? No, we're looking for absolutes. Does anybody notice there's something wrong? What do you notice wrong, Connor? Yeah, this point is actually not on my interval. So even though I wrote this down here at the bottom, I actually shouldn't have. My notes are wrong too. Our absolute maximum occurs at the endpoints on both of these. It's actually an absolute maximum of negative 3 at x equals 1 because 3/2 is actually outside my interval. Yes, sir. Correct. The 3 over 2 is not in the interval. Right, like if you were thinking like a number line, here's my negative 2 and here's my 1. This is the interval I'm supposed to be looking between, but 3/2 is over here. Yeah, a little bit weird one. Sorry about that. Process is still the same though. You're looking for the value that's the biggest and the smallest on the interval. Okay. We've done 2 polynomials, so we should really take a look at something that's not a polynomial and see how that affects things. And this is an example of one. So what kind of a function is this? What do we call it? Somebody knows what it's called. Not linear, definitely not a line. Huh? Nope. Not linear, not polynomial. It's called rational, as in it's a ratio. Yes? Yeah, it is. It's a rational function. It does have a location where the derivative doesn't exist, correct? Where does the derivative not exist here? Yeah, at 2. So that is one of our critical points. So as I'm doing step 1, the directions here are the same as the last one. There is a critical value at 2. It's probably still going to have an asymptote there, the entire time, but just be aware of the fact that the derivative doesn't exist there. The second part, which is to find the derivative equal to 0, we still need to do. I do have a quotient rule on this one, so it's not a simple rule like the last two, but it's not a terribly awful quotient rule like some of the ones you've experienced. So we have the denominator times the derivative of the numerator, which is what? 1, minus the numerator, which is t, times the derivative of the denominator, which is also 1. And it's divided by the denominator, t minus 2 squared. So you can see I'm still not going to be able to plug t equal to 2 into this function, right? I'm still going to keep getting asymptotes here as I continue. If I simplify, clean this up just a tiny bit, I have t minus 2 minus t over t minus 2 squared. And you'll notice, of course, the t's in the numerator cancel out. So I have negative 2 on top and t minus 2 squared on bottom. And we're supposed to be answering the question, where does this equal 0? Right? That's what it said for critical numbers. So where does it equal 0? Okay, why do you want to reciprocate? To
That'll like negative 2 on top and the denominator having a variable in it.
Okay, so if
But
you...
since it's 0, you could just do that because it's going to cancel out either way. So, or you can just...
Okay, I think what you mean is to multiply by the denominator. Is that what you mean?
Yeah, make it...
Okay, so yeah, what we could do is you could multiply both sides of your equation by t minus 2 squared to eliminate the denominator, because then you won't have it at all. But what happens on the right-hand side when you do that? You get 0. What happens on the left-hand side? You get negative 2. So what does that tell you? You can't do it. There's no way for this function to equal 0. So you can think about it from that perspective of if I were to try to cross multiply, basically, which is what I kind of did there, I would actually end up not finding a solution. You can also try, or you could also perhaps, especially since I'm mentioning it now, remember that in order for a rational function to equal 0, it's the numerator that has to equal 0. Because the denominator, no matter what it is not going to make the whole fraction equal to 0, ever. I can't divide by something and get 0. Think about the division facts. Every time we divide, we always still have something left over, smaller than what we had normally, right, if we're dealing with bigger numbers. But I still have something. I never get 0. So there's no way for this numerator, negative 2, to equal 0. So there's no solution here. That is to say that there's no critical point. Okay? So there's only one critical point, and we know at that critical point that our function actually has an asymptote. So that's not especially friendly. However, it's also worth noting, because I didn't note it before, that 2 is not on my interval, is it? It isn't. So as I'm trying to do step 2, where I would try to evaluate the function value at the only critical point I have, f of 2, this does not exist. So I don't have a critical number value point. I don't have one to test. The only thing I can do is to move on to step 3, which is to test my endpoints. So I would find f of 3 and f of 5. They aren't f's, they're h's, aren't they? So h of 3 and h of 5. So take your calculator if you wish, or you might be able to do this one in your head pretty quickly. If I plug in the number 3, what will my function equal?
3.
It's 3. And if I plug in 5, what will my function value equal? 5/3 is correct, yes. Awesome. Which of those is bigger? Which one's smaller? We'll start with the absolute minimum. Which one's smaller? The 5/3. So the absolute minimum is 5/3. And it occurs at x equal 5. And the absolute maximum is 3. And it occurs at x equal 3. The absolute maximum, the absolute minimum are y values. Always a y value. They occur at a particular x location. All right, we've got one more to take a look at. Same directions, but as I've said before, gotta have some trig, right? It's important for you to sort of realize with trig functions, just standard cosine sine in particular, that they're oscillating functions, right? They go up and down. So there's going to be lots of places where they have relative maximum and relative minimum points. So this idea of having an interval where we're looking between two particular values is really practical for this kind of a function because all it does is keep going up and down, right? And so I need to have a limited viewpoint because I couldn't even find all of the locations where it has peaks and has valleys very nicely. So let's take a look at this one. Cosine, as you know, it's a wave function, right? It's sinusoidal is what it's called. And it's smooth, it's continuous like a polynomial. There's no asymptotes involved or any of that kind of mess. So I don't have any locations where it's not differentiable, all right? But the other part of that, finding where it's equal to the derivative is equal to 0, I will have. So what is the derivative of 3 cosine x? Good, -3 sine x. And we're going to set that equal to 0. So it's nice enough that I can actually recognize that I divide by -3, right? It doesn't affect the actual locations of where sine is equal to 0. The other thing that's worth noting here is that I really am going to eventually have to go back to the fact that I'm on the interval 0 to 2 pi. So I only need sine values that are 0 between 0 and 2 pi. All right, so one rotation of our circle, or within 1 unit circle. So where in the world is sine equal to 0 between 0 and 2 pi? At 0, pi, and 2 pi. Which is interesting because it's actually happening on the endpoints of this one, right? That didn't happen on either of the other examples that we did. But it can. It could happen that the interval's endpoints actually coincide with critical numbers already. The reason that's sort of helpful is because when I do step 2 to test these points, I will test g of 0, g of pi, and g of 2 pi. But on step 3, there's nothing new to test. Step 3 is already done once I've done step 2 because the endpoints are already done. So grab your original function, 3 cosine x, and we're going to plug in 0. We're going to plug in pi, and we're going to plug in 2 pi. So what happens when I plug in 0? I get 3. What about when I plug in pi? It's -3. And 2 pi? It's 3 again. And as we've talked about, that makes sense, right? That it repeats itself. We've got this kind of an image going on. So I have the minimum. I have 2 maximums in this case because of where the endpoints fell. So there's actually a couple of locations of absolute maximums. My absolute minimum is what? It's -3, and it's occurring at x equals pi. The absolute maximum is what?
3
3.
at 0 and 2 pi.
Yeah, and it occurs at x equals 0 and 2 pi. Does that make sense to everyone? Awesome. All right.